Hi everyone, my name is Drgona, and together with my colleagues Aaron Tuor, Elliott, Skomski, Soumya, Vasisht, and Draguna Vrabie from Pacific Northwest National Laboratory, we are happy to present today our latest work on deep learning for explicit differential predictive control applied to buildings. Our main motivation is based on success stories of classical model predictive control in application domains such as process control, automotive, aerospace, or more recently, high-performance robotics like this Boston Dynamics Atlas robot. But in all of these applications, there is underlying assumption on a reliable and accurate system dynamics model. But this assumption is being challenged in non-traditional applications of MPC like building controls or power grid systems, where modeling is subject to unknown or partial known dynamics, or just purely physics-based modeling is too expensive with given narrow economic margins. And on the other hand, purely data-driven models, they lack generalization, they don't satisfy physics-based constraints, and they require a large amount of data set, which are typically not available in practice. At the same time, there are issues with real-time optimization on a very large systems, computational limitations of the control hardware on the edge, or parallelization and distributed optimization of model predictive control for distributed systems. To motivate this a little bit further, let me walk you through implementation of the white box model predictive control in real office building in Belgium, which was done back at KU Leuven, where we have been dealing with large office building, 5 floors with more than hundreds of occupants, and we approached this from physics-based perspective. So we first studied the technical sheets of the building, envelope, HVAC system, and designed this high fidelity emulator using Modelica language. And then we extracted this large state space control-oriented model with more than 300 states and designed the classical model predictive control in MATLAB using LMIB and constraint optimization solver Vrabie, and deployed everything online, real-time optimization using cloud-based SCADA system, where we have been overwriting the set points for these building management systems on 15-minute sampling intervals. So from the performance perspective, this was a great success. We achieved energy savings of more than 50% and improved comfort by almost 40% compared to classical static rule-based control. So there is no doubt that there is potential for advanced model predictive control applications in building controls. However, at this particular implementation case, the whole design and deployment was very complex. You basically need to have an army of PhDs to design your high fidelity model, design model predictive control, and deploy online in cloud-based system. So we started to ask questions. Can we simplify things by using modern machine learning methods? And the first thing was to use so-called approximate model predictive control, when we basically imitate the behavior of our MPC in simulations and approximate this behavior in neural network. This approach basically improves the deployability of the controller by reducing the memory demands, dependencies on commercial software, and it's much faster during the inference because all the computation is done offline and you are just doing evaluation of your functional map in a real-time implementation. However, there is the one fundamental disadvantage. You are still requiring on original model predictive control with original model of the system, which you need to design first to generate your training data. So we are not really solving the problem of the modeling with this approximate MPC approach. Then we start asking questions. What if instead of imitating the supervisory MPC, could solve the MPC problems while learning the system dynamics at the same time? So that's the idea behind this differential predictive control, where we construct this differentiable closed loop system dynamics as a composition of our neural control policy and neural system dynamics model to be able to learn both at the same time or sequentially given the real-time measurements of the system. And there are some nice theoretical connections with model predictive control. I want to go a little bit deeper. When in classical MPC, We are solving standard form optimization problem, given objective function, equality, inequality constraints in real time. Online, we are recomputing this problem given new measurements of our system states. There is an alternative. We can also do it in Lagrangian form with this hard constraint problem. We put constraints in our objective and use barrier or penalty functions, but still it's online optimization problem. A third way how we can deal with constraint optimization problem is so-called parametric programming, which is a very neat idea of basically pre-computing a solution map for this standard optimization problem, given some set of parameters theta. And these parameters now represents, let's say, our initial conditions, our states, or our bounds and constraints, or references. The disadvantages is that classical solvers for parametric programming based on active set enumeration or geometric approach, unfortunately, don't scale to very large state spaces. So they are like beyond the application space of this large scale optimization, like in buildings. So we start asking questions. Can we use machine learning to approximately solve this parametric programming problem? And typically people think of machine learning as unconstrained optimization. Here I would argue we should think of machine learning as constrained optimization. For instance, like if we have this model, and it be the linear regressor, polynomial model, or even neural network, these are our equality constraints. And yes, we are learning those parameters with respect to data, so we can bend the behavior of the model to our will, but this is pretty much our structural assumptions of what we are going to learn. And if we fix some layers of this model of, let's say, neural network with some known constraints, then it's becoming a little bit more of the standard optimization problem. At the same time, we can use various regularization in the loss functions. We can include Lagrangian penalties to enforce inequality constraints during the machine learning process. And many success stories in machine learning are basically built on adding more and more fine-tuned regularizations or more structural priors in the neural architectures to target specific application area. So this is pretty much in line with this approach, what we call data-driven differential parametric optimization, where we combine the principles of Lagrangian optimization and machine learning to basically solve this parametric programming problem in data-driven way. So in a little bit more detail, we are aiming to solve this parametric optimization problem given nonlinear objective and subject to inequality equality constraints, while as opposed to classical parametric programming, our parameters theta are not given as some set. They are given as a distribution of the data samples. And now the objective is to find the mapping H, which maps these parameters theta to some optimal decision variables. And in control, this theta can be initial condition of your states, and optimal decision can be your control action, and this H can be neural network control policy. So in the last almost 2 years, we have been working on developing software solutions using modern machine learning libraries like PyTorch for basically implementing these constraint optimization problems with high levels of abstraction, such that users familiar with YAML or CVXPy can use these type of modeling abstractions to formulate and solve these data-driven optimization problems. So to give you a little bit of teaser applications, what you can do with this differential parametric optimization is to learn model predictive control policies, or these differential predictive control policies for known unstable system. So let's have this unstable double integrator subject to state and input constraints, and we want to optimize this quadratic MPC loss. Then we formulate this differential predictive control with this MPC loss by appending in the loss function the penalties on our penalty functions, which can be straightforwardly modeled by, let's say, by ReLU functions in neural networks, subject to our neural network architecture, which is given as a closed loop dynamics, be given by this linear state space model and nonlinear control policy. And we have this data set Xi, which represent our parameters of this problem. And now, as opposed to classical MPC, when we would be searching for optimal trajectories or control actions, now we are searching for optimal weights of the control policy that parameterize this control problem and minimize this loss function over the distribution of our parameters. So on the right-hand side, we have a demonstration how we can stabilize this unstable system just by means of offline optimization and learning control policy, which stabilize the states, but at the same time satisfy the constraints of on the control actions. And when we compare side by side the control policy loss landscapes with solutions obtained by multi-parametric programming toolbox in MATLAB with this differentiable parametric programming using this PyTorch-based framework, they look pretty much similar and satisfy constraints uniformly. So this is very encouraging, and that motivated us to look at much more challenging control problem of economic DPC for building applications, which was done in this paper. Here the setup was as follows. We had this high order building physics emulator representing of like almost 300 state space RC network for building envelope, convective heatful equations, representing the HVAC, and pre-computed nonlinear weather influence, which represented like 40 disturbances affecting the system dynamics. So we assume that we have access to this time series data of open loop behavior of the system. And in the first step, we learn this structured system identification model, which basically represents a neural state space model, where each of those blocks can be parameterized by either linear map or neural network. So a little bit into more details, we have been using this observer fully connected neural network, which was mapping past trajectories of our states, observed states into initial conditions of our latent states, which represented temperatures within this building structure. And we use this Hammerstein model to basically represent our state update with nonlinear inputs and disturbance dynamics modeled by neural networks. Then in the second step, we use this trained neural network model together with neural network control policy representing fully connected neural net in this closed loop differentiable MPC structure, and differentiated the MPC loss function, in this case economic loss, minimizing energy use and control penalties, to find the optimal weights of our neural control law. So how do we perform in a closed loop system when we are training this offline and deploying online? The results have been pretty encouraging for a case without planned model mismatch, where on the left-hand side, we have state trajectories to be controlled within certain prescribed bounds. So we have 6 zone temperatures, and on the right-hand side, we have the 6 control actions representing mass flows. And what we can see, like state and input constraints are satisfied most of the time, basically obtaining this large-scale explicit controller with suboptimal performance. So, but before you get too excited, there is still work in progress, because when we deploy this on the plant with the plant model mismatch and significant additive disturbances on the top, we needed to incorporate corrective feedback controllers to basically compensate for this feed-forward control policy of differential predictive control. So this is pretty much an open problem which we are working on right now, and we are leveraging some ideas from offset-free model predictive control by extending our state space model, augmenting the states with integrators to achieve tracking and closed loop stability of this economic differential predictive control offline during training. So as a conclusion, I have presented differential predictive control, which is a viable candidate for classical model predictive control approaches. It's a data-driven method based on neural state space models. It allows us to incorporate constraints, learn explicit neural control policies, and we are leveraging nice theoretical connections with model predictive control for uncertainty quantification, planned model mismatch, stability, convergence, and constraint satisfaction in our ongoing work. If you are interested in more technical details, please visit our open source repositories, and we are happy to receive the feedback. Here, I would like to thank you very much for your attention.